Even now, I meet some of my colleagues from IIT, and they are still talking about the rank that they got in the JEE exam. And I find it kind of absurd that you have accomplished so much in life, you have done a lot of other things. How does one exam? The exam cannot actually capture totality of your personality. Secondly, doing original research or starting a business or doing some social construction, leading a company, the kind of skills that are required, kind of abilities are so completely different. And they're simply not captured by this very mechanical hundreds of problems that are solved. So, this idea of sorting people, which is very much deeply ingrained in IIT, and it's, in my opinion, it's extremely poisonous actually. This is, if the students are watching, that this is not the purpose of education. Sandeep and I took those books in summertime home, and we basically studied it from cover to cover. We said, okay, this is quantum mechanics. We want to understand quantum mechanics. And so this is how we really helped each other. I remember going and talking to Witten saying that I wanted to work on string field theory. But already the interest in string field theory was waning. So I started to work with Lance Dixon, who was a young assistant professor. He was a student of Jeff Harvey. And he gave me a problem which had no solution to work on. He asked me to prove something which actually is not true. So I failed to prove it, which was good because if I had succeeded in proving it, I would prove something wrong.
Hello and welcome to Intellectual Rigor. Our guest today is the Indian theoretical physicist Professor Atish Dabholkar, the director of the Abdus Salam International Center for Theoretical Physics in Trieste, Italy. His celebrated career began with a master's at IIT Kanpur and a PhD from Princeton University, where his foundational work on supersymmetric solitons, now known as Dabholkar-Harvey states, helped pioneer the study of string theory dualities. After a long professorship at the Tata Institute of Fundamental Research (TIFR), Professor Dabholkar became renowned for his work on black holes. He made outstanding contributions by establishing how quantum theory modifies a black hole's entropy, culminating in a remarkable discovery with Samir Murthy and Don Zagier that connected this quantum entropy directly to the mock modular forms of Srinivas Ramanujan. You have seen a few powerful moments from our conversation, and they hint at the remarkable story behind these achievements. Today, we trace that full journey. How does a boy from a small village in Maharashtra, immersed in a family of rationalists and social reformers, find himself at the absolute epicenter of string theory revolution at Princeton? Let's get to the interview. Professor Dabholkar, welcome and thank you for taking the time to speak with us today. It is a privilege to have you with us.
Thank you. Yeah, it's a pleasure for me to be here too.
Thank you, sir. Thank you so much. Thank you for giving us your valuable time. And I'm quite sure that when students watch, they would definitely get inspired and benefit from this interview. So, sir, let's start with with your childhood. Let's begin with your origins. Your family background is remarkable, with your father and uncle being prominent figures in science and India's rationalist movement. How did this environment of high level science and social consciousness shape your perspective on the purpose of science?
Yeah, no, thank you. So, no, it is true that I grew up in a somewhat unusual family, and my parents were. I didn't realize it when you were growing up because that's what you see. But when I look back, I did have, compared to my contemporaries, I would say I sort of grew up in a quite a progressive household.
Mhm.
So, my parents' generation was this generation post independence who, with a certain sense of idealism about, uh, you know, national reconstruction. I grew up in a small village near Kolhapur in Maharashtra, so I speak Marathi. Uh, and in a way, when I look back, it was a very useful and interesting experience. So there was a rural university which was started after independence by some very prominent educationists and intellectuals of India. One of them is J.P. Naik. So J.P. Naik is actually very well-known educationist. His name appears in the UNESCO's roll call of the most important 100 educational thinkers of the last 2000 years. He's actually not so well known in India, but he
Yeah.
was a very influential educationist who
Mm-hmm.
dedicated himself to creating sort of, India was kind of completely destroyed during the colonial rule. So, really, rebuild the institution was a major challenge. And so, this institution was started, Mauni Vidyapit, it was called, with the motto was development through education. And it received, because JP Naik and other major intellectuals like Acharya Bhagwat, they were involved. It had
Mm-hmm.
also funding from the central government. So it was actually a central government funded university. And the idea was to create a university in rural India to bring modern education and science to independent rural India. And JP Naik identified my father and my mother as one of promising young people who could be inducted. And so they were both
Okay.
professors in this university. My father taught statistics and mathematics, and my mother was a professor of sociology. So it was quite a unusual university because of its mission and because of the people who were involved, at least in the beginning. But of course, it was not like a elite. So I grew up with, in my class, my best friend was a son of a
Mm.
small farmer, and my other best friend later on became mechanic in state transport. So I just grew up without any real academic pressure. I didn't have to, I mean, I did very well in school. I was always top of my class and so on. In the SSC, I came third in the state, the entire Maharashtra state at that time.
Okay. Okay.
But there was no impetus from home. Like, my parents never asked me to study. I mean, they sort of, it's not that they were neutral about it, but they didn't
Mm.
force me to focus on school curriculum. I mean, we had a
Mm.
very rich intellectual atmosphere. We had lots of books. I read a lot,
Mm.
and I
Okay.
interacted, I argued, I studied. But it was
Mm.
not oriented towards, because of their general philosophy was like that. Education is not for just to get a degree and a stamp. It should really be a process of learning. And
Mm.
so, because of that, I think my approach, attitude was quite different. Even when I got into IIT, then I went after 10th standard to Ferguson
Mm.
College in Pune to study, because the village school was not good enough for. And then I applied for
Okay.
IIT. But I remember my father or my mother never asked me, are you studying for IIT? Which class are you going to? They basically left me to my own devices. I think I subscribed to this lecture notes that used to come on a postal course. And I was pretty much falling behind. And I don't know how actually I got into IIT. I mean, if I look at now this
Oh,
quota model and the way people prepare, I just
yeah.
did it on the side, and I got into IIT. So this was the general atmosphere at home, that somehow there was no emphasis on formal education, but more on education proper. My mother and father, they met each other there. So again, it was slightly out of caste marriage, a love marriage in those days. So, like, you can imagine, it was very unusual in those days. My mother was actually not religious at all. So we sometimes
Puja. Or,
celebrated Ganesh, but more as a cultural Diwali. Of course, we celebrated all this, but there was no religious. So I would say I sort of grew up in a very atheist kind of progressive household. They
Mm.
were, a lot of these people were influenced, of course, many as Mahatma Gandhi, by his
Mm.
social commitment. But I would not say that they were Gandhians. I mean, my
Mm.
father was quite committed to modern science. So he was,
Mm-hmm.
both of them were not in a traditional sense Gandhians or something like that, but
Mm.
this influence of Gandhi, that somehow what you're doing should have some reflection upon the society in which you
Mm.
live in. This
Mm.
did make an impression on me. Then my father, even though he was a professor of statistics and mathematics, his hobby was horticulture and agriculture and gardening, but not just as a hobby. He had actually studied it in great detail. And
Mm.
At one point, he left the university, actually, this university, because he got disillusioned, even though it was had inspiration from people like JP Naik. He felt that this was not actually delivering development through education. It was actually preparing students for, I don't know, I mean, for civil engineers. Okay, they were being trained properly to build bridges. But a large number of people were basically left out of this stream of science and knowledge with a stamp of failure. And he felt that in that way, the university was not actually fulfilling its mission. And at the same time, he promoted this major movement called the Prayog Parivar. I think later in his life, he received a lot of national and international recognition. So he got the Jamnalal Bajaj Award, which is very prestigious, when he was 55. But he was also appreciated his thinking and his approach by JP Naik himself, who was, of course, a very well known educationist. But then other major thinkers internationally, like Ivan Illich, who wrote this famous book on deschooling society, and Paulo Freire, who wrote this another famous book called Pedagogy of the Oppressed. My father had the opportunity to interact with them quite strongly. He basically was able to organize in through this Prayog Parivar several small farmers in this western Maharashtra, and they started grape cultivation, which was a very unusual crop for that part. But my
Yeah.
father was doing his own experiments, and he was able to get 15 bunches of grapes in a small. So he was sure that this can be done, and when he was, of course, doing it for a hobby. But when some of the farmers learnt about it, they were fascinated, and they wanted to try it out on their own land. I know many of them. Some of them were only fourth standard, but they were really thinking like a doctoral scientist, doing very careful experiments, really understanding the science behind it. So it became like a spontaneously organized people science movement, and thousands of farmers later on joined this movement, and they started to produce hundreds of crores of grapes and exporting them from a region where previously there were no grapes.
No grapes.
So this
Yeah.
was a remarkable achievement, and it had very much to do with science for the people. And he translated, I remember, I mean, just to give you how it must have influenced me, he translated a major monograph on viticulture. Viticulture is the
Okay.
grape cultivation, general viticulture. It was written by Winkler, I think, from University of California. So this is really
Okay.
considered a standard textbook for all the University of California viticulture classes. This is like one of the
Okay.
classics in this field. And the question was that can relatively uneducated, I mean, so this was the connection with the university experience, that people who are thrown out of formal university, they were actually able to pick up this knowledge. So my father translated this 500-page monograph into Marathi. And I actually remember when I was 11, 12 years old, was I was helping him to do the translation. And there are all kinds of complex concepts, how does photosynthesis work, how to use gibberellic acid to get, there is a lot of science behind it.
Mm.
And the idea was that can this science be picked up? And this was a demonstration that this can actually be done. And this certainly had a big influence on me.
Great. Can you tell us what specifically sparked your interest in physics and how that led you to make a deliberate choice to pursue it at IIT Kanpur or later? Like what sparked that? Because you have, I mean, father is interested in agriculture, horticulture.
Rural
He's a professor.
construction,
At,
reconstruction. It's
yes,
not
yes, yes.
so. It's not exactly the path that would take you to some very abstract field of theoretical physics. Which
Mm,
so this was. It's true that, but my parents were like that. That they really did not. We were three brothers, and they really did not
mm,
insist on any particular. They did not tell me that okay, you should do computer science or you
ah,
should do
mm,
engineering
mm,
or do medicine, do physics.
mm,
I remember in the part of the reason, and this is for the maybe the students who listen to it. I mean, part of the reason
mm,
is there is a bit of romanticism. When you are young, you actually don't know enough. You don't know whether you are actually have the capability. You see, it's like you want to become a cricket player. You
Mm.
might be good at cricket playing, reasonably good, but to become a
Mm.
cricket player and to make a career in cricket is not the same as playing cricket at the school level. So I was, of course, very good in. I was doing well academically. As I said, I came third in the state without too much effort because I was in this village school and I was not training very hard for this exam, and I came third. So I was I was naturally good at mathematics, and of course, I was reading about Einstein and quantum mechanics, relativity. I mean, so these were intellectually very, let's say,
Stimulating to.
stimulating, and there is also some kind of intellectual glamour associated with it,
Yeah.
which captures your mind when you're a teenager.
Mm.
And I wanted to do
Mm.
that. So I decided in 11th or 12th that I want to do physics. And fortunately, I had a very good teacher, a mathematics professor in university in Ferguson College, M. Prakash. So he really guided me in a way. And he had done his PhD from IIT Kanpur. So he told me that for physics in India, you should really go to IIT Kanpur.
Okay.
And of course, I wanted, in a way, as at that age, I also wanted to get away from my parents in a little bit. So my parents were asking me, why don't you go to IIT Mumbai, which is nearby? But I said, no, no, my professor has told me IIT Kanpur is the place to go to. And then, of course, then I will be farther away from them. So I will be more free in a way. And I'm just, in a way, I'm not saying that was the motivation. But so I decided to go to IIT Kanpur. And I remember my father said that, and my mother, that they said, okay, you do what you want to do. Just be aware that this is a difficult career, maybe 10 years down the line, your friends who are in engineering or medicine or
They.
IT, they would be making 10 times your salary. Are you okay with that? I said, I'm okay with that. I said, okay, it doesn't matter.
Mm.
I'm not trying, I don't know. It's not that I want to become a research physicist and
Mm.
get prizes. I just want to pursue physics. It's not like I'm thinking of myself as becoming some star and or becoming
Mm.
like a test match cricket player. I just
Mm.
enjoy doing physics, and I'm happy to follow whatever comes with it. So I think I would say it was a very good style of parenting. I mean, I know many of my other friends in IIT, they were sometimes forced by their parents to do engineering or to do
Yeah.
technology or to do computer science, whereas they wanted to do something else like linguistics or physics or mathematics. And they were not able to do it. And in the end, actually, in a way, you have to follow your heart.
Mm.
But there is also a caution. I mean, one should not, what they call the survival bias, that
Mm.
it's not a good example for me to tell people what you should do, or I don't like to uh, say that, follow your heart, because one should also take some of these practical considerations into account and not just say that follow your heart. So what my father used to say, that you take a calculated risk. You take a
Mm.
risk, but take a calculated risk. Try to understand what you're getting
Mm.
into and not just say that, okay, I'm going to become the next Einstein. I mean, the glamour is necessary also,
Yeah.
but it's a good idea that at that age, 15, 16, you're still very young, but you are already becoming an adult and you are capable of sort of taking responsibility for. So I would say
Mm.
that this was very good parenting, that they sort of gave us the freedom, but they sort of made us aware of the responsibility that in
Mm.
the end you have to make your living and be aware. So, for example, my elder brother wanted to have his own business. This is again very unusual given our background. We were, but he said, no, I don't. He got into actually IIT Delhi, but he said, I don't want to do PhD. I want to have my own business. And so he
Okay.
actually started his own hospital. I mean, so he worked to get experience in some construction company and things like that.
Mm.
And but he was completely, and this is in Gujarat, I think it's more common to go have entrepreneurship. In Maharashtra,
Mm.
it's less so. Especially in the family circle of family that I came from, they were
Mm.
more academically oriented or social construction. These were their priorities. And so, so my elder brother started his own hospital, and I think I remember my parents supported it equally. telling
Mm.
him that, okay, look, I mean, we are middle class family, so we cannot take financial risks of the kind that you may want to do. But my brother again said, I'm happy if I have a business which is selling bhel
Not.
puri, but I want to have my own business.
Yeah, it's.
So I think it's a good, yeah, so it was I would say it was good
Mm.
parenting. I was fortunate, I would say, to have that.
Sir, give us some idea about your bachelor degree, your graduation and post graduation. Based on my research, I understand you went to IIT Kanpur as your professor prescribed that is the best place to do physics and learn physics.
So I did this 5-year MSc program. Immediately after my 12th, I went to IIT
Okay,
Kanpur for 5 years.
okay.
And I should say that it was a reality check for me because my first three physics courses I got a C. So all my friends were getting A. So I
Hmm.
was not even getting a B, I was getting a C. Part of it is that
Okay.
because I had some difficulty adjusting to the language because I grew up in this
Hmm.
small village. I studied in Marathi. My Marathi was very good, as I mean, I wrote also literary pieces in Marathi, but I
Okay.
was not comfortable
Hmm.
enough with English. So
Hmm.
it took
Hmm.
me 2-3 years to really adjust my thinking to the new language.
Hmm.
And being in a very competitive environment like IIT,
Hmm.
but I had some really excellent professors there and very excellent
Hmm.
colleagues. I mean, my very good friend Sandeep Trivedi. So actually, one of the
Hmm.
great things about college education and places like IIT is really even more than the curriculum, your peers. So Sandeep Trivedi, he's also a theoretical physicist, a well-known theoretical physicist. He became the director of Tata Institute of Fundamental Research. So we were extremely close friends,
Okay.
both as friends, but also we were the two people in IIT who were totally passionate about physics.
Oh,
And
okay.
we went and talked to some of the key professors, like as soon as we had the opportunity, telling them that we would like you to teach us this course in quantum mechanics to make sure that we got the best professors. And so Sandeep really had a big influence, I would say, on my career and on
Yeah.
my life because even though he was my contemporary, and I, likewise, I think vice versa. And
Hmm.
some of the professors like Professor A.P. Shukla, Professor
Hmm.
Mani, they had a
Ah.
very big influence on the way we both sort of grew in our
Hmm.
understanding of physics.
So, during your time at IIT Kanpur, perhaps during the master's or bachelor's time, did you kind of narrow down that this is the area of physics that I'm little bit more interested, I want to study, pursue it further? Because during the end of master's degree is a time when you start deciding what should I do next. Like, should I do go for a PhD? And if I should go for a PhD, where should I do that? PhD degree.
I guess I was fortunate to have had Sandeep as my, and also IIT general ambience is quite competitive and people wanted to go to
Hmm.
do PhD in the US. In those days, that was really kind of the
Hmm.
thing you wanted to do.
Hmm.
So that way, I was guided in that direction naturally. But also,
Hmm.
Sandeep's elder sister is also a physicist, Nandini Trivedi. So he had sort
Hmm.
of a home background about the path you take, to take a GRE,
Hmm.
which are the universities you want to apply to, and so on. So that kind of helped me indirectly.
Hmm.
But
Hmm.
it was pretty clear to me by the third year. I mean,
Hmm.
I remember after my second year, so even though I kind of did miserably in the first physics courses, after a while I started to find my grounding, and then I
Hmm.
started doing very well. Uh, uh, because I think also there is a big difference between doing well in exams. So I told you about my father. His thinking was picked up when one of the seminars in New Delhi, there was Ivan Illich. He has written this
Hmm.
famous book, Deschooling Society.
Hmm.
So he invited my father to come to Mexico, and there he met some professor from Germany. So that German professor invited my father to Germany, and he
Hmm.
organized a major seminar together with Paulo Freire, who wrote this famous book on pedagogy of the oppressed. He made a
Hmm.
major contributions to literacy in Brazil, and
Hmm.
he was in fact exiled by the military junta in Brazil. So he was a so this German professor organized a 2-day seminar on science for rural development with
Hmm.
Paulo Freire and Shripad Dabholkar. So they were the two
Hmm.
main speakers, and
Hmm.
his idea was to put these two concepts sort of in comparison with each other. That Freire's idea was that education should become a means of emancipation. I mean, that's why the military junta exiled him, that people should really learn for themselves. So he was quite against critical of this method of sorting people. Most
Hmm.
of the exams, what they do is they sort you for life, that you have
Yeah.
this rank or you have made so much. And it's actually quite absurd. I mean,
Hmm.
and I've when I look back, I find how fortunate I was that my parents were not like that. That even now, I meet some of my colleagues from IIT, and they are still talking about the rank that they got in the JEE exam. And I find it kind of absurd that you have accomplished so much in life, you have done a lot of other things. How does one exam? The exam cannot actually capture your totality of your personality. Secondly, doing original research or starting a business or doing some social construction, leading a company, the kind of skills that are required, kind of abilities are so completely different. And they're simply not captured by this very mechanical hundreds of problems that are solved. So, this idea of sorting people in this, which is very much deeply ingrained in IIT, and in my opinion, it's extremely poisonous actually. This is like
Hmm.
if the students are watching, that I don't think this is not the purpose of education.
Hmm.
So this element was there in IIT very much so, but slowly I've sort of clearly found what I wanted to do, and it's clear that doing research in theoretical physics is completely different from solving, let's say, problems in physics or maths Olympiad. I mean, there are tough problems, let's say, in physics or maths Olympiad. I never took the Olympiads, but I know people
Hmm.
who have done extremely well in Olympiad, and of course, they have strong capabilities. But you
Hmm.
see, there you are solving, or in JEE exam, you're solving some very well defined problem which has a
Hmm.
well defined solution, and you have to solve it in a fixed amount of time. In the research, it is much more open ended. Or starting a business, it's a very open ended. You're sort of trying to figure out what is the interesting problem. You're sometimes thinking about it for years, not for 3 hours, but maybe 3 years or 10 years. That this is an important problem, and then you're trying to learn the techniques that can bear upon this problem. It's not very different. Let's say if you want to start a new business, you cannot just say that, okay, I will do this. There is no clearly defined manual that gives you do this, and do this.
And highly collaborative effort, right?
First of all, it's collaborative. It requires
Hmm.
multiple skills and multiple influences.
Hmm.
It requires an ability to commit yourself to some long term goal, which is not tested.
Hmm.
This ability is not tested in a JEE exam. So
Hmm.
I remember that somehow, I mean, thanks also to the professors and my colleagues like Sandeep. In the summer of my second year, so by that time, I
Hmm.
was beginning to really get excited about physics and really understanding what physics
Hmm.
is all about. So I remember during that summer, he and I took the 2 volumes of quantum mechanics by Cohen and Tanuji.
Okay.
Cohen Tanuji is a Nobel laureate. It so turned out by a funny coincidence that when I was in Paris, he became my next door neighbor later on in life. It was just a funny coincidence. But Sandeep and I took those books in summertime home, and we basically
Hmm.
studied it from cover to cover. We said, okay, this is quantum mechanics. We want to understand quantum mechanics. And so this is how we really helped each other, that we started to
Hmm.
feed off on each other, and we were basically talking more to each other than to the classes. So by the time the quantum mechanics course was taught, we were already well prepared. And
Hmm.
in my fourth year, then I went to Tata Institute of Fundamental Research as a visiting. So by that
Hmm.
time, it was pretty clear I wanted to work in theoretical high energy physics. I did a nice project with Professor S.M. Roy on
Okay.
magnetic monopoles and Dirac fermions in the presence of a magnetic monopole, which is actually has
Okay.
interesting consequences for proton decay. This is known as the
Hmm.
Kalon-Robakov effect. So already in my fourth year end, I was being introduced to research level topics. I remember
Oh.
asked to read the very famous paper by Witten on supersymmetry. So I started to already get excited about, and so these names you started to learn, Callan and Witten, and they were at Princeton, and everybody in Tata Institute told me that, okay, there is this exciting thing happening in string theory. Already some big revolution, string theory revolution had happened. The first 1984. I was in 1984 in Tata Institute. So I obviously wanted to go to Princeton. I mean, and I was very competitive, of course, and I fortunate it's also one of these uh, accidents in a way that leads you. So I got admission into Princeton. I was one of the first few Indians, actually, first Indians to go there. There were not many students from India in Princeton in those days. And Sandeep went to Caltech on the other coast.
Okay.
And after a few years, we swapped places, actually. I went to Caltech for my postdoc and he went to Princeton. But so I think for me, already by master's, I was pretty set on my path. I mean, I wanted to do not only physics, but I knew what aspect of physics I wanted to study. And there was this famous paper, the Princeton String Quartet, it was called, on the heterotic string theory by Gross, Harvey, Martinic, and Rome. So I had the good fortune to take courses from all these people like Callan, Witten, Gross, and Harvey. And then Harvey became my PhD advisor.
Jeffrey Harvey, your
Jeffrey Harvey. So,
advisor.
So this was, in a way, I was quite fortunate, I would say. It was a straight path, sometimes it doesn't always work out like that. So I sort of wanted to do something, and this was the university I wanted to go to, and I just got in, and I got to work with the people I wanted to work with. So I would just say that it was a piece of good fortune.
I mean, 1985, it was a height of first superstring revolution. Can you describe the atmosphere at Princeton during that time? What was it like being a young student at the absolute epicenter of this incredible intellectual explosion in physics?
So first of all, as I said, later, some of, I mean, I guess I can take some credit for it. But I think basically people figured out that students from India are quite good, and especially from IIT Kanpur. So after a while, Princeton had many students from, and some of them have done extremely well. Rajesh Gopakumar, then Ashwin Vishwanath, Shiraz Minwala. So many people started to come to Princeton from India. But I was really the first one. I mean, in a way, there was maybe somebody else before me 5 years before.
Okay.
And India in those days was not so open. So, for me, it was really like a culture shock. I remember at 12 o'clock at night, midnight, I was dropped in the center of Princeton by the shuttle from the airport. Of course, this is a famous place. You had heard about it. Einstein lived here and so on, and all these my heroes. So it was somewhat of an intimidating experience, but actually, I was very well prepared, I thought. I mean, sometimes people in Princeton have this big difficulty in adjusting, but I didn't have. I cleared the exams very quickly, the general exam and so on. So I was totally prepared in terms of my intellectual preparation. But of course, it was quite a fantastic experience to learn quantum field theory from Callan and Gross and Harvey, and then to learn general relativity and string theory from Witten. So it was a very rich experience, and I had the fortune to write papers with them, interact with them at multiple levels. So they also became like colleagues and friends, and later in my life. But it was, yeah, you're not sure, as a graduate student, you don't know where you stand, and as you said, it was really the epicenter. So it was really happening like that, that really exciting papers were coming out almost every month, every week. I mean, Witten alone was probably writing a paper. So those 2 years were extremely, extremely productive peak in Princeton, actually. Even by standards of Princeton, those 2 years, 84, 85, 87, there was huge explosion of activity. And you sort of wonder that, is this what is required to be a reasonable physicist that you have to write all these papers, exciting papers. So you begin to doubt a little bit that, okay, I mean, is this what is expected? But then it happened that by the time I actually started to do my own research, somehow there was a
mm,
big reaction against string theory, let's say from people in
mm,
Harvard, Georgia, and Glasgow. And string theory also got a little bit stuck after 87, which always happens. I mean, there is big
mm,
excitement, then you discover difficult problems. And so it was not clear what kind of research problem I should work on.
mm.
I remember going and talking to Witten saying that I wanted to work on string field theory, but already the interest in string field theory was waning. So I started to work with Lance Dixon, who was a young assistant professor. He was a student of Jeff Harvey. And he gave me a problem which had no solution to work on. He asked me to
Okay.
prove something which actually is not true. So I failed to prove it, which was good because if I had succeeded in proving it, I would prove something wrong. But then Lance moved to Stanford, Slack. He got so he decided to move to California, and therefore
Okay.
then he asked Jeff Harvey that, okay, I have this student. I have told him to prove this, but he hasn't really succeeded. But maybe he's not bad. So then I started to work with Jeff Harvey, and we ended up writing a paper which turned out to be quite important later in
Yeah.
about superstrings and solitons and proving
Mm,
some non-renormalization. And Jeff was a very good advisor in that he sort of left me to my own devices to some extent. I mean, he was also quite free. He was not telling me to do this or do that, which is
mm.
sort of suited my temperament. And then when I was in my fifth year, he actually moved to Chicago.
Okay.
My last year, I was pretty much by myself. I mean, interacting with him by email.
Okay.
But we wrote this I think, which became an important paper on superstring and solitons. We were the first to conjecture that some kind of string duality. We found
Mm,
some solitonic solutions of string theory, which we didn't quite understand. We found some spectrum of states, which are now known as this Dabholkar-Harvey spectrum of states,
yeah.
which have some very important properties, which later on became important for duality, symmetries,
Mm.
and also for the exploration of black hole entropy.
You have described this work as a first love and ahead of its time. I kind of gather that from some of the
Yes.
research. What did it feel like to be working on something so fundamental whose full importance might not have been immediately obvious to a wider community?
Yeah, I think that's a very good question. That research is quite like a Brownian motion. You start doing something, and then you actually end up doing something else. But you sort of have some
Mm,
general idea about where you want to go. And this
mm,
idea of solitons, membrane solutions. In fact, I made a mistake in a way, research wise. I mean, so I did
mhm.
not pursue the consequences of this work as much because
Okay.
somehow then matrix model became very popular when I was just
Mm,
graduating, and nobody was paying attention to our paper, and I was a bit disheartened by that. Of course, people like Jeff Harvey and Kurt Callan, who were more experienced,
mm,
they pursued with it. I mean, so actually I got also an offer to work to go to Santa Barbara and to Harvard,
mm, mm,
and where Andy Strominger was
mm,
really pursuing these ideas of membranes and dualities, something which we had conjectured and which we had originated
mm.
in some ways. But I said, no, now I want to do something different.
Oh,
I want to prove myself in a different. So I kind of more deliberately moved away from my own research. Of course, I came back to it later on, but perhaps
mm,
if I was a little bit more experienced, I would have pursued that line of thinking more uh, and gotten more out of it. So
mm,
this idea of developing your own ideas,
mm,
even when the community is not paying attention to it, was difficult for a young postdoc. I mean, so I sort of got sucked into a little bit the current fashion of the day, which was matrix models. And I
mm,
think in hindsight, actually, the work on solitons and membranes turned out to be far more important than, I would say, the
Hmm.
work on matrix models, because it really opened the way for duality symmetries and black hole physics.
Dualities.
Yeah.
Yeah. It's different. Sir, after Princeton, your postdoctoral journey was a grand tour of theoretical physics like Rutgers, then Harvard, and then Caltech, right? How did the different intellectual cultures at this institution influence your thinking and your research style?
No, I think it's a very good question, because each place has a different style of doing physics.
Mm,
And there is
mm,
something to be said about, like, Princeton has a certain style. It's
mm,
quite, you really, you think of an idea, you develop it, you write a paper, all the calculations are done.
mm,
So it was good to be trained in that tradition. But
mm,
then Rutgers had this more kind of open-ended culture, that discuss a lot and you work together. Steve Schenker was quite
mm,
influential there for me, and Tom Banks,
mm,
with whom I wrote
mm,
papers, Nathan Seiberg, Dan Friedan.
mm,
So there was
mm,
this very Zamolodchikov, all
mm,
the top string theorist, Michael Douglas, and later on Greg Moore, I think, and many of them I ended up writing papers with. They became my collaborators. But that style of doing physics was a bit different from the one in Princeton. Then I went to Harvard for just 1 year, but Kamran Wafa, who was more in the Princeton style. So,
mm,
but and again, a different way of doing physics. And
mm,
then Caltech was another different experience. There were John Schwartz and John Preskill. So in a way, till 1996, so after I
mm,
graduated in 1990 and until 1995, instead of developing these ideas of solitons and duality,
mm,
which I should have
mm,
done, I
mm,
was trying to do something else, like matrix models, which also later on became useful, and trying to
mm,
compute entanglement entropy, string theory, black hole physics. So actually,
mm.
I got interested into black holes and entanglement during this period, which again
Okay.
became important 15 years later.
Later in
So
India.
it's, yeah.
Yeah.
So I think, and black holes actually became important immediately. So I
Mm,
think, yeah, it's a kind of a crisscross of influences. So by the time I went to Caltech, I had my own research program in a way, and I wanted to work on
uh,
entanglement. I wanted to work on dualities. And in 1995, there was a major breakthrough again,
mm.
where there was a strings conference in
Professor
University of
Witten.
Southern California. Witten kind of wrote, gave his revealed his major
M.
breakthrough on string dualities and M theory.
Mm,
But there were antecedents, very major important antecedents, with the work of Ashok Sen
mm,
and with the work of Hull and Townsend and John
mm,
Schwartz and many others, which had built up to this string duality. And before that, there was work in duality in the quantum field theories with the work of Seiberg and Sen, and again many others,
mm,
which had prepared the ground for this rather remarkable symmetry, that
mm,
theories at weak coupling, when the coupling constant is
mm,
very small, can be at strong coupling look completely different than their weak
mm,
coupling.
mm.
So theory A and theory B, which look very different at weak coupling, can somehow be the same
Be the same.
manifestations at different values of the coupling constant. So the
Mm,
famous example, of course, is the type 2A M theory duality, where at strong coupling you even have one extra dimension. So a
mm,
10-dimensional theory can be dual to an 11-dimensional theory, and things like that,
mm,
which were
mm,
unimaginable, I would say, 5 to
mm,
10 years ago, would have sounded almost absurd to believe in. The community and the works of various people somehow gathered sufficient evidence to make this kind of a symmetry possible. And then in 1996, there was again major breakthrough with the work of with Sen and Strominger and Waffa in black hole physics, which developed into the holographic symmetry that of Maldacena and
mm. Johan Maldersen. Mm,
Juan Maldacena, and then Gupser, Klebanov, Polyakov, and Witten. and again many others who later contributed to it.
And that was the year when you kind of decided to return to India and
Yes,
join
so it was
TIFR.
clear. Yeah, I always wanted to come back to India. That was clear. So at Caltech, actually, I had this 6 year position. It was almost open ended. I mean, so I also had some offers for tenure track positions, but I was quite sure that I wanted to come back to India. So I could have stayed on in Caltech or gone to some American university, but I really wanted to come back to Tata Institute. So I was very happy in Tata Institute. There was such a nice setup. So I didn't feel that intellectually I was losing anything.
How was the scientific environment at TIFR at that time, and what role did you hope to play in shaping it, in other direction, like maybe improving that in some sense what you learned from,
Yeah, I think, just making whatever intellectual contribution I could make to help
mm,
build the science community in India,
mm,
because you realize that, of course, the most important thing is people in the end. So
mm,
if you cannot create a scientific community just by having institutions like Tata Institute, I mean, you have infrastructure. And I think, fortunately, by the time I came there, Tata Institute was being noticed. They were beginning to have an impact in the central
mm,
part of physics. Thanks to
mm,
many people there, Spenta Wadia, and also the director of the time, V. Singh,
mm,
they supported this. Then there were younger people like Gautam Mandal, who was my contemporary, Avinash Dhar, and
mm,
Sunil Mukhi, Shumit
mm,
Das, Ashok Sen. So there
mm,
was a really a strong group together. So on a daily basis over lunch, you could talk about physics
mm,
and the latest development. Also, because of the internet nowadays, everything was available. It was not like you had to get some preprints being sent from Princeton or Caltech or
mm.
Harvard. And so immediately we were in the thick of things. So I think that way, internet and this archives really made a huge difference to the way science was
Huge.
being done. Yeah. So I was very happy. Then I mean, first of all, slowly, I mean, for example, we held the Strings Conference 2001 in
Think
India
concept.
for the first time in a developing country. And in a way, it was a recognition. I mean, I was together with Sunil Mukhi and Spenta Wadia was one of the main organizers, but the entire string community was behind it. And
Mm,
it was a kind of a recognition by the international scientific community that the string theory community of India is mature enough and is
yeah.
strong enough to hold such a conference. It was not, in those days, it was not so easy, getting
Mm,
flights and funding for flights. And we
yeah.
got basically all the leading figures in the field to come to India.
Edward Witten, David Gross,
Hawking came, then also Jeff
Hawkins also. Yeah.
Harvey, John Schwartz, Michael Green.
Yeah.
Yeah, many others also from the younger generation like Oguri.
Mm. This period led to one of your most celebrated achievements. Your work connecting quantum black holes to Ramanujan's mock modular forms. The story goes that it all started with a hunch when you invited the number theorist Don Zagier to a physics conference. Could you walk us through that moment of intuition? What made you suspect that the answer to a deep physics problem might lie in this esoteric branch of pure mathematics?
Yeah, so that actually happened later in Paris. So I was at Tata Institute from 1996 to 2007. Sorry,
Mm,
2010. But
mm,
in 2007, I moved to Paris. I mean, mainly for personal reasons because my wife is from Slovenia. I met her in 2003, and we were trying to figure out a place where we can both be together. And turned out then the Paris was kind of a compromise solution, meaning where we could both find employment.
mm.
So I went to Paris for that reason. I was quite reluctant to leave India, but I mean, it was not like I was looking. I was quite happy at Tata Institute, and then in Paris, we had, for example, Don Zagier, with whom I collaborated. He was at Collège de France
Mm,
at the time. So
mm,
in a way, I was more naturally connected to that community. Perhaps from India would have been a bit further. And I would say it was very natural for me to invite him, because
Hmm.
many of these modular forms and Jacobi forms and some of these objects which are loved by number theorists were
Hmm.
beginning to make their appearance in the counting of black hole microstates. And the reason for that is basically not hard to understand, is that two-dimensional conformal field theories naturally have modular symmetry, is one of the symmetries
Hmm.
of a two-dimensional conformal field theories.
Hmm.
And this just follows from the fact that if you have diffeomorphism invariant and
Hmm.
Weil invariance, then that diffeomorphism and Weil invariance together uh, leads to modular symmetry. And since
Hmm.
any physics theory has to be diffeomorphism invariant, which means that, and if it is a conformal field theory, then it's also Weil invariant. There
Hmm.
is naturally a modular symmetry, and therefore modular symmetry, which is a group SL to Z. It's a group of 2 by 2 matrices with integer entries, with some determinant being 1, some properties. But
Hmm.
this is a very, very deep and very central field of research in number theory, going back to Poincaré and Ramanujan and many. It has a long history and a very celebrated history. It comes in the context of physics because of conformal field theories.
Hmm.
Modular group naturally arises. And in
Hmm.
many other different contexts related to the physics of black holes, conformal
Hmm.
field theories appear naturally. So that's the
Hmm.
connection between black holes and this kind of esoteric mathematics. That
Hmm.
so black holes have some entropy,
Hmm.
and anything which has entropy can be explained in terms of the microstates of that system. Like, for example, the
Hmm.
gas in this room has entropy,
Hmm.
and that corresponds to the way all these molecules that are moving around in air can
Hmm.
organize themselves. So the number of ways, number of microstates in which this different trillions of molecules can organize themselves. So some molecule could be going that way, another molecule could, or some other ways. That, if you take the logarithm of that, that gives you the entropy of the room,
Entropy.
the entropy of the. And so basically, the entropy of a black hole, which is a very beautiful result uncovered
Hmm.
by the work of Hawking,
Hmm.
gives you a window into the microscopic structure of the black hole, because it is telling
Hmm.
you, it's a logarithm, that quantity that which you can compute is a
Hmm.
logarithm of the number of ways in which the microstates of black holes can organize themselves. And
Hmm.
those, so the number of ways is a number, right? It's a number of
Hmm.
ways
Yeah.
in which, in a more technical way, it's the dimension of the Hilbert subspace. I mean, it's some
Hmm.
space of states, and how many states are there is a number, and that
Hmm.
number can be calculated, and
Hmm.
that number turns out to be related to some coefficient of some modular form. So that's
Hmm.
the
Hmm.
connection with number theory, that these numbers that occur in describing the physics of black holes also are the numbers that occur in number theory for different reasons.
Hmm.
So, for example, Ramanujan was interested in this problem because if you take a, let's say, take a number like 5 and
Hmm.
ask how many ways you can partition this number.
Hmm.
So it's a very simple combinatoric problem. You can
Hmm.
write it as 5, or you can write it as 4 plus 1, or you can write it as
Yeah.
3 plus 2, or you can write it as 2
Hmm.
plus 3, or 1 plus 4, or
Hmm.
you can write it as 3 plus 1 plus 1. So there are
Hmm.
some number of ways, let's say 12. So you would say that the number of partitions of 5 is 12. I don't know
Hmm.
if it's 12, but let's say 12.
Hmm. Hmm.
Now you ask the question, how many ways you can partition 100? That number is
Hmm.
actually enormously big. It's exponentially
Hmm.
big. And Ramanujan
Hmm.
figured out a very clever way of calculating that number together with
That
Hardy.
part.
So this is the Hardy-Ramanujan formula,
Hmm.
Hardy-Ramanujan-Rademacher formula, that tells
Hmm.
you how this simple problem, combinatoric problem, how to partition an integer into many different integers. That problem turns out to be related to these modular forms. So that's the long connection. So it's
Hmm.
some kind of a counting problem gets related to some
Hmm.
counting problem is naturally related to some number theoretic problem, and that
Hmm.
counting
Yeah.
problem is related to this modular objects like modular forms,
Hmm.
Jacobi forms, and later mock modular forms, which is what
Hmm.
Don Zagier, Samir Murthy, and myself, we worked on. So it's really a beautiful and unexpected connection that this Hardy Ramanujan formula also plays a very important role in understanding the quantum corrections to the entropy of black holes. And so it's a kind of quite an amusing, and I was not so mathematically inclined that way. I mean, I would not have thought that I would write a big paper with a number theorist with theorems in it. But I sort of was naturally led to these questions, and it turned out to have a very pretty mathematical answer, and which also has a pretty physical interpretation. So I think, yeah, it was a fun collaboration.
How does the, I mean, for our general audience, broader audience, what does it tell about the deep structure of quantum gravity and space time? Like, what kind of light does it throw on it?
I mean, it shows that there is some quantum nature. The fact that, for example, the entropy of a black hole is given by the area of the surface of the black hole. So basically, the entropy of a black hole is area divided by 4 in some units. So area is the surface of the black hole. But the area can be any real number. But as I said, entropy should be the logarithm of some integer. And the question is that on one hand, you have a real number, on the other hand, you have a integer. Of course, when the integer is very large, then the logarithm of the integer can look like a real number because you cannot see. If you change the integer from 1 million to 1,000,001, the logarithm doesn't change very much. So in the large area limit, you cannot really distinguish between the real number and integers, or finely spaced integers. But if in quantum gravity you really want to be see that integer, and what was nice is that in our work we were able to, in some toy examples, we were able to simpler context, we were actually able to calculate all the corrections. There are actually infinite number of corrections to this area formula, area upon 4. There are corrections which go as 1 upon area, logarithm of area, exponential of the minus area, minus the area. We were able to calculate all of them, and magically they sum up to an integer. So in a way, this physics of the black hole reveals some kind of an integral discrete structure of space-time, which is not so that's why it is related to quantum structure of space-time, because if you look at the area, it's a smooth quantity and it can be take any real value, but somehow the entropy of the black hole manages to see an integer in that particular context. But this also, of course, links to a much broader story of holography, that there is somehow the information about the black hole is captured by the surface of the black hole, and this kind of discrete information can be captured by the surface of the black hole. This is, I think, the lesson, I would say.
It kind of tells us that nature at the fundamental level, space time has a discrete nature as opposed
has
to.
a discrete nature, and that's what it is. In a way, this is the quantum structure of space-time. So I think these are a few examples where these kinds of calculations are possible. In most of, even in holography, in most cases, you're not actually able to do this kind of exact calculations. It's a very, in a way, very specific, very symmetrical configuration where you can do these calculations. But it's a kind of a proof of concept that there is this discrete structure underlying gravity, which is, I guess, one of the lessons of our results.
One more question on the science side. Like as a string theorist, I mean, of course, we all, based on our understanding, imagine, visualize space time. As a string theorist, how do you visualize space time at the fundamental level, and what do you see there? Like what's happening out there for the general audience?
I think it's really, the picture is not very clear at the moment, I have to say. Meaning, if you had asked this question in the 90s, you would have said that at some very short distances, electrons and photons, they're really like little pieces of strings, and you will see that structure. But now we believe that there can also be other solitonic objects like membranes, which are playing a role. So the picture is much more complex than, and much more interesting than what we had imagined. And I think it's quite clear that there is something very deep new structure is there that needs to be explored. But I
Oh,
would say that we are quite far from making immediate contact with experiment or
yeah.
understanding in the same way, let's say Einstein understood the principles of general relativity. We are not at that
Mm,
stage yet, or people have understood quantum mechanics. We
mm,
are in string theory, we are still far from that stage. But already what has been revealed is quite fascinating. That, I mean, I have taken this analogy sometimes that it's a little bit like coming across some beautiful temple, and you're an archaeologist, and you uncover, it's like, suppose Angkor Wat, when you suddenly are digging somewhere and you find that it's actually some beautiful pillar of some temple. And then you discover that that pillar, it's actually part of a big complex. And
okay.
you see one sort of part of the temple is general relativity, other part of the temple is
Mm,
quantum mechanics. But
quantum.
somehow the two things are connected through this structure that you are beginning to uncover. But we still have not completely uncovered that structure. So we can see that there are pathways going from the quantum mechanics side of the temple to the general relativity side of the temple. But we don't
Mm,
know where is the kind of the sanctum sanctorum of the temple, where
mm,
uh, it's a very big structure. And so I think it's a yes, but it would be foolish to stop digging. It's like that I think some people should keep digging. It's not to say that everybody
mm.
should therefore start digging here, but I think
Uh,
there is sufficiently strong hints that there is some quite a beautiful architecture which is connecting the known theories that we believe in. But in what way they are connected, this is not
yeah,
fully understood.
yeah, yeah. Very nice example. Some people should dig there, and some people should dig around that place, nearby places, so they might find something new and new
So, yeah, they
connections.
might find something else. Yeah. So I think string theory is not, I mean, also the paradigm of how we do science has changed, because doing
Mm,
experiments to quickly verify your ideas, I mean,
yeah,
this kind of a simple idea that we had in the 19th century, that, okay, you make a theory, you make a prediction, and you do an experiment and you change your theories. That's really already, if you look at the Higgs boson, I mean, it took 50 years
yeah,
and
50 years.
$10 billion dollars and a huge accelerator. Physics actually doesn't proceed like that anymore.
Mm,
It's a more complex assessment of a theory.
mm,
What is a important theory, what you want to pursue, is not determined in the simple minded way that is sometimes presented in
mm,
some sophomore course in history of science. And one of the reasons why we continue to pursue this kind of exploratory science is because
mm, mm,
there are extremely strong hints of these interconnections, which simply
mm,
cannot be accidental.
mm,
Simply because the whole picture is not clear. It would be, for example, gauge theories, quantum gauge theories, which are the basis of
mm.
the standard model of particle physics. Whether
Model.
you take
Mm,
strong interactions, weak interactions, they are related, we believe and we understand in some cases in quite great detail, to
mm,
gravity. This is a completely
mm,
unexpected connection. And this kind of a connection doesn't come about by accident. That's why it's like you don't come across a beautiful pillar in the middle of
mm.
nowhere by accident. If you are coming across it, it means that there is a bigger temple complex that must exist. And that's why
Yeah,
people explore this. I think some people continue to explore these aspects of quantum
yeah,
gravity.
yeah, yeah, yeah. There is a strong intuitive reason why still people are exploring that. Okay, let's bring our discussion to your current role as a director of ICTP. So your journey seems to have perfectly prepared you for building on Abdul Salam's legacy. How do you see the role of institutions like ICTP in fostering global equity and cooperation, especially with new scientific revolutions like AI on the horizon?
This International Center for Theoretical Physics, which was founded by Abdus Salam, a Nobel laureate from Pakistan, 60
Hmm.
years ago,
Hmm.
when some of my serious colleagues sort of asked me that I should consider becoming the director because they were looking for a director. And I was quite
Hmm.
reluctant in the beginning. And I mean, of course, these are people whose opinions I value greatly. So I gave it some serious consideration. But
Mm.
Part of the reason is that ICTP really has a very unique mission, and I
Mm.
can sort of identify in some ways with Salam. I mean, Salam also, grew up in a small village in Pakistan, like I did. Of course, he grew up in
Mm.
a more Islamic household. I mean, he's quite religiously inclined, not like my childhood. Then he went to Cambridge and he returned to Pakistan because he wanted to contribute to. So in that way, I can identify these motivations and theoretical physics, also intellectually. And he made these very major contributions to one of the most important pieces of the Standard Model, together with Glashow and Weinberg, electroweak theory. So in a way, what string theorists are doing is a kind of a continuation. It's in the same intellectual stream. So
Mm.
both intellectually and from his social commitment point of view, I could identify
Okay.
with him. And
Yeah.
ICTP's mission really deeply resonates with me at a fundamental level. And that was one of the reasons I returned to India, that I wanted
Mm.
to be a theoretical physicist, but also contribute in some way to the society in which I live. And ICTP directorship sort of offers that opportunity on a
Yeah.
global scale, and which is why I decided to take this role. And I think I'm very happy with the. I mean, I follow Salam's advice to keep the morning free for physics, so that unfortunately ICTP is not such a huge operation. It's not like a big university. It's not even as big
Mm.
as the Tata Institute of Fundamental Research. So the amount
Mm.
of administrative responsibilities or leadership role is not that overly time consuming. I mean, you can still find good time for doing research.
For your own research.
And at the same time, its mission is so unique that, and it is, of course, a very highly regarded, high profile institution, UN
Mm.
organization. Its its mission is what, so I don't mind. Therefore, I really feel sort of at some deep level, at a psychological level, it gives me great satisfaction that I'm able to contribute to
Mm.
global science or making
Mm.
scientific opportunities globally available. Having this aspect, this mission of ICTP really has sort of, I feel, is very close to my heart. And I think if I'm able to make some contributions to that, it's kind of very rewarding at a personal psychological level. Because,
Yeah.
as I said, given having grown up in India, in a way, I have seen sort of a whole cross section of society, from
Mm.
small farmers in a small Indian village, and then in places like Princeton, and where while they
Brilliant.
are intellectually great places, they're also very, very privileged places.
Mm.
Can the scientific opportunities, it's not good if they remain locked to this very
Locked.
privileged,
Very few.
very few. And I
Mm.
mean, there can be Ramanujans who are not able to participate. So
Mm.
from that point of view, I feel really very strongly motivated to. So I don't never feel that when I'm doing something for ICTP, I'm sort of wasting my time or it's some bureaucratic thing, because I see that there
Mm.
is a big, grand mission which is of extreme importance, I
Yeah.
think, in today's world. And
Mm.
I, of course, things have changed. So I sort of did some soul searching after becoming the director, or actually before accepting to become the director. And I came to the conclusion that ICTP's mission is still very fundamentally valid today. It has to
Mm.
be done differently than how Salam was going about it, because times have
Mm.
changed, as you said.
Mm.
We are no longer looking for the Higgs boson.
Mm.
The right frontiers of science have changed, but also the
Yeah.
geopolitics has changed. I mean, India, China, and Brazil are not developing countries in the same way. So I recently actually got the strategic plan of ICTP approved. And I
Okay.
had identified three priorities in that. One is, of course, the ICTP core, to make the
Mm-hmm.
ICTP's core strong. And on that front,
Mm.
we managed to get some major grants from the Italian government and
Mm.
Simon's Foundation International, Arab Fund, Kuwait Foundation, to really strengthen the ICTP's core competence. But then the other two is, one is International Science Alliance, which is philosophically a bit different. I mean, it's inspirationally is the same as what Salam wanted to do. That
Mm.
ICTP has this UN mandate. We can bring
Mm.
countries together through science, through
Mm.
doing science.
Mm.
But I feel that now we can do it more as equal partnerships rather
Mm.
than which used to be a bit more unidirectional at the time of Saddam. That, ICTP was, it was also a little bit patronizing, I would say. See, nowadays, China and India have such strong, or many countries have very strong scientific communities in certain areas. And it's
Yeah.
not like the first world is offering something to the third world. It's more like both worlds can actually benefit. You can benefit
Mm.
from the strength of the Chinese, let's say, progress in AI, or the India's
Mm.
string theory community. So I think I look at it more. So that's why I've been calling it an international science alliance rather than it's an
Mm.
alliance. And I'm very happy that we have succeeded to get the involvement of governments like the Brazil. I signed recently
Mm.
some agreement with Brazil, many major universities in China, in India. Recently, I was visiting Romania. I met with the president
Mm.
of Romania. So again,
Mm.
Eastern European countries would not be considered developing countries, but it's not
Mm.
so much. It could be that somebody in Sofia in Bulgaria, a
Mm.
young scientist there, would benefit a lot more from the existence of ICTP or the programs that we offer than somebody working at Tata Institute, where the so what you regard as, I think, so therefore we look at this mission of ICTP in a broader way, that any place which that we want to make the resources, scientific resources, available to everybody,
Mm.
irrespective of where they are. It could be in Ethiopia, or it could be in Sofia, or it could be in Mumbai, or let's say in
Mm.
Indore. Also in India,
Mm.
there is a lot of fluctuation, there is a lot of variation.
Yeah,
There are
certain.
top places like Tata Institute, but if you go to Kolhapur, where I grew up, the resources are not the
Mm.
same. The place like ICTP is still kind of an inspiration for many
Mm.
scientists from all over the world to come. We receive 6,000 scientists every year on our campus, which is quite a
Oh,
lot. I
okay.
mean, so it's a huge. So this is the mission of ICTP, is to combine scientific excellence with global inclusion, and that
Mm.
aspect really appeals to me. And the
Mm.
third mission, the sort of third strategic priority which I have identified, is the International Consortium for Scientific Computing, to address
Mm.
exactly the issues that you're raising, that open science in the coming years will not really be effective if you don't also have open access to computing. So the fact that all the computing resources are currently locked in a few places is not, I mean,
Mm.
even if people have access to the on the cloud, on the computing, just to know the
Mm.
technology, how to do the programming, how to use the
Mm.
algorithms. So
Mm.
I see a huge role for ICTP in this regard, that to extend the notion of open science to include open computing, because even in areas like theoretical physics now, it's going to be, I'm not a computational physicist. I do pencil and paper calculations. But the next
Uh-huh.
generation is going to be more and more involved with computing. And I regard it as a kind of a obligation for ICTP to make create these opportunities. And it's a huge task because ICTP is too small. The kind of resources that are available with even private companies are just mind boggling. So that's why I thought about Scientific Computing Alliance. And we have been successful again to have very good, very substantial agreements with corporations like IBM. We recently started two major prizes, Brahmagupta Prize for AI and Feynman
Mm-hmm.
Prize for quantum computing, together with IBM.
Okay.
Organizations in Switzerland or South Africa. So I think we are really trying to build this international consortium for scientific computing. This is one of my priorities. Let's see how well we succeed on that. So I
Yeah.
think on these fronts, I would say ICTP is responding to the new challenges and the new areas of science that are coming up, and also is
Mm.
responding to the changing geopolitical situation. And once
Yeah.
again, here I see a huge role for ICTP, because now some of the almost the existential threats, like the climate
Mm.
problem, the climate
Mm.
response, really requires
Mm.
global cooperation.
Yeah.
So, for example, ICTP has used to have the monsoon workshop for 10 years, where
Mm-hmm.
scientists from China and India and Pakistan and Nepal, from this region, can
Mm.
come together to discuss the monsoon. Now, where in the world can you do this? The ICTP is the only
Mm.
place where you can do this. You cannot
Mm.
have a monsoon workshop in India where the Pakistani or Chinese scientists can come. It's very difficult visa wise, etc. Vice versa. But monsoon really doesn't care about, and the science doesn't care about, and the nature doesn't care about it.
Care
So
about.
the boundaries. So I think
Mm,
I really see that ICTP can play a very major role. And that
mm.
has been my sort of what, in a way, has been one of my drives for doing something substantial for ICTP.
That's really important to bring the equity to the forefront. Yeah. This interview is for the young people out there thinking about a life in science. Looking back at your journey from a village in Maharashtra to Trieste, what is the single most important piece of advice you would like to give to brilliant young students who is full of curiosity but perhaps is unsure of the path ahead?
Yeah, I would say that you need both a little bit of foolishness, I mean, sort of a little bit of romanticism or passion
Mm,
about what you're doing. Otherwise, yeah, you don't want to be too practical about things. So I would
mm,
say that, okay, it's good to be excited about these things. There are really exciting frontiers. But I think
mm,
it's also good to, one thing I can say is that, for example, in India, the reason I went into theoretical physics was partly because I really didn't have good models for people doing experimental. I mean, experimental physics is not that emphasized in our
mm,
educational system,
mm,
or let's
mm,
say exciting things that are happening in other fields of science. So it's a good idea to keep an open mind. I have seen it a bit in myself, and also I see it among the students that, okay, sometimes people say, okay, I want to work in string theory, but actually you don't
mm,
really know what is string theory all about. The right
mm,
approach is that you say that you want to work in some broad area of theoretical physics where there are exciting problems that are soluble. Sometimes
mm,
the fields also can have difficulties. Certain fields like superconductivity, and you
mm,
cannot say that I want to work on superconductivity, because
mm,
high temperature superconductivity, the theoretical understanding is still not complete, and maybe breakthrough will not
mm,
happen immediately in 2 years
mm,
when you want to do your PhD. So I think you have to keep an
mm,
open mind about where are the opportunities, what are the
mm,
exciting areas where you can make a contribution. I think that's the most important thing, that one has to figure out what you are good at and
mm.
in what way you can contribute. And if you do that, then I think you can be productive and also happier, because
Yeah.
you're not trying to be somebody else. I think when you're choosing your career, it's good to have some passion about certain areas of physics, but I think you should keep a slightly broader outlook and not be fixated about, okay, I want to do superconductivity, or I want to do, because you don't
Mm,
actually know enough by the time you're beginning to
mm,
make that decision. Or I
mm,
want to do string theory, or I want to do general relativity. It's not, but you can keep this broad perspective and then choose the right areas
mm,
as they come along, as they present themselves. And
mm,
oftentimes you end up doing some relatively small problem in a big, you're not going to start a revolution in your graduate studies necessarily.
mm,
And that's not what you should be looking for. I think what you should be looking for is where you can make a contribution. For example, some people are very strong mathematically, some people have
mm,
strong physical intuition. I mean, there are different styles of doing physics, and you have to figure out
mm,
where you can make a contribution. If you try to be like somebody else, it's not going to work. So see, I think this is also a generally good advice for
mm.
life, is that I
Yeah.
always ask myself where I can make a contribution. It can be a very small contribution, but I would rather do a small and concrete contribution than just talk about some grand things. And
Mm,
so the same approach I take towards my contribution to ICTP, that okay, if I can make a difference in some small areas of where ICTP needs strengthening, that
mm,
that way I'm accomplishing something rather than
mm.
just talking about things and criticizing things. And
Yeah.
so I think I would say that be passionate about things, be a bit foolish about your passions, but be also
Mm,
realistic about them, and don't be completely foolish about them, and try to understand where you can make a contribution. It's a bit like in cricket. It's like, I don't know,
mm,
Sachin Tendulkar wanted to be a a fast bowler. You see, and he would have been always disappointed in his life if he tried to be a fast bowler. His physical attributes and his abilities were such that he was meant to be a batsman and not a fast bowler. Mm. Now, he was fortunate that he discovered that, it could be that he actually spent, and that's not always possible. It's sometimes, so, if you're off spin bowler and you're trying to be a batsman, then it's not going to work. Yeah. Similarly, maybe you are good to be an engineer, maybe you're very good at engineering. So don't try to become a theoretical physicist. Or maybe you are really like a number theorist, think like a number theorist. Then don't try to be like a physicist. I mean, so I think discovering what you are good at, and that's process, I think, is always ongoing. I mean, actually nobody knows, even I, what you are good at until you have tried it out. So I think that would be my general advice. I generally don't like to give general advices. No, but that's quite valuable, and it actually, yeah, even Professor Abhay Astikar told the same thing when I asked him the question. So, to conclude our conversation, I have a few quick rapid fire questions. Just
Okay.
first thing that comes to mind. What's your favorite equation? I would say two, Dirac equation and Einstein's equation. Okay. And Maxwell's
Einstein's
equation. Maxwell's equation.
and
Yeah.
Maxwell's equation.
That covers pretty much everything.
Pen and paper or computer for thinking?
I think for me, it's pen and paper.
Majorly pen.
But I think some people are good at working and thinking together with a computer. Yeah, I don't think you can substitute. I don't think AI is going to substitute sort of conceptual thinking in theoretical physics, but it can be a major help if it is used in the. And some people are good at it. I'm not very good at. I'm not good at numerical work, but some people are very good at it. So I think again you have to find out what you are good at.
If you could travel in time to meet one scientist for a day, who would it be and what would you discuss during this meeting?
Actually, I wouldn't particularly care to, because the kind of problems that I'm currently interested in, I feel that the scientists of the past would not have very much useful to say about them. So, for example, I mean, of course, it would be wonderful to discuss with Dirac about when quantum mechanics was being discovered. But now that we know quantum mechanics, I don't think, for example, Dirac kind of did not quite understand quantum field theory. The modern approach to quantum field theory, the renormalization group, he sort of, similarly, Einstein did not quite understand quantum mechanics. Of course, I fully understand that he made very, very deep contributions to quantum mechanics. But from the modern perspective, I'm not sure Einstein's views would be particularly useful to know for a modern physicist, because he does not have the perspective and the background about what has come after them. So I think I would like to move away from the person to the work, really, because I really feel that science is a much more of a community exercise than it is appreciated. Sometimes I think these prizes, like, I don't know, Bhatnagar Prize or Nobel Prize, you single out one or two individuals, but there is usually 20, 30 people who have contributed some major breakthroughs. Many of these ideas are such that even if Einstein was not born, what he discovered would be discovered. Or if Dirac was not born, what he discovered would be discovered. So I'm a little bit against this bit of hero worshipping, which is in physics, we are actually very much into this. We want to think about and we want to say whose contribution is bigger, and that is a useful exercise. But I'm not so much into it, honestly.
Okay. One book every young scientist, every young researcher or student should read, in your opinion, for physics, general physics, I would say.
I think, of course, most people might give you this answer. I think Feynman's lectures, volume 1 and 2, are really wonderful, and they remain. I think for a student to get started, I cannot think of something better.
Something better, yeah. That's true. Most beautiful idea in physics, according to you?
No, there are so many, so it's really hard to, whether it's
Choose.
Einstein's idea to really understand that defining time, to understand that everything is really, it's really kinematic idea of how you define time that leads to Lorentz transformation. That was a very simple and yet very beautiful idea, or principle of equivalence. But at the same time, I'm also deeply impressed by, for example, the way Dirac has formulated quantum mechanics. That's the formulation we use, all this Bra and Ket, and it's again, in a way, Heisenberg and Schrodinger had discovered the quantum mechanics, but the way we actually approach it now is the way Dirac had formulated it.
Yeah.
So, but in quantum mechanics, yeah, so again, there are many beautiful ideas. I mean, the fact that the energy is quantum and that information is quantum, I mean, quantum coherence. So, yeah, it's difficult to, if you want to ask simplicity and depth, then I think principle of equivalence and perhaps idea that time is relative is one of the most shockingly simple ideas to state, but it has this amazing consequences.
Last quick question. If you could solve one mystery in the universe, what would it be?
I really think that, I mean, for currently, I would say dark energy is something which is really, to me, a big mystery. And I feel that I have made some efforts and I have failed, I would say. But I really think that there is something about the long distance structure of gravity that we don't understand. And I somehow feel that some of these problems, I mean, we have been focusing mostly on the short distance structure of gravity. This quantum gravity, holography, string theories all goes in the direction of short distance structure of gravity, where there are all these fascinating questions about entanglement and black hole physics and so on. But I also think that there is something fundamental that we don't understand about long distance structure of gravity. How does de Sitter, the universe that we live in with a cosmological constant or maybe with dark energy, to me, yes, resolving the puzzle of dark energy would be a very, very big.
So, Professor Dabholkar, your journey and your insight have been incredibly illuminating. On behalf of all our viewers, especially the young students, thank you so much for being so generous with your time and for sharing your story with us. Thank you.
Thank you, and all the best to you.